Look at this heavyweight fist, suspended just a fraction of a millimeter before it violently collides with its target. When an amateur boxer throws a heavy punch, they generate around 2,500 newtons of compressive force. That is equivalent to balancing 560 pounds of weight onto a single point of impact. At the elite heavyweight level, the kinetic output scales dramatically. A world-class strike transfers over 1,600 joules of kinetic energy directly into a target. That energy does not originate in the arm. It begins at the floor. The kinetic chain relies on sequential force summation, starting with ground reaction force driven by the lower extremities, transitioning into hip torque, and compounding via trunk stabilization. Every ounce of that rotational momentum is channeled into the fist, and the entire transfer of mechanical energy happens in an incredibly narrow window, between 60 to 100 milliseconds. Mike Tyson provides a perfect case study for this mechanical system. Weighing 220 pounds, his physical mass acted as the raw fuel, and his mechanics converted that body weight into maximum terminal velocity. Producing 1,600 joules of kinetic energy creates a catastrophic physical contradiction. The human body is capable of generating forces that its own skeletal structure cannot naturally survive. The impulse momentum theorem dictates that force equals the change in momentum divided by the change in time. Graphing this inverse relationship shows that to maximize peak force, impact time, delta t, must approach zero. A faster collision yields a more violent force. The biological boundary condition in this physics equation is the human hand. The metacarpal and carpal bones are relatively thin, fragile structures. Under normal circumstances, applying over 1,000 pounds of instantaneous compressive load directly to these small bones will shatter them completely. The hand must conduct its massive kinetic payload into an opponent's skull without absorbing the reciprocal peak force that bounces back along the arm. At these energy levels, the boxing glove serves as an engineered velocity conductor, an energy attenuator. By artificially extending the impact duration by a few crucial milliseconds, the glove preserves the strike's overall kinetic energy while dropping the peak reciprocal force to a survivable level. To understand how those milliseconds are bought, we move past the macroscopic exterior of the glove and into the microscopic environment of the padding inside. Modern gloves utilize high-density polyurethane foam. Structurally, this is a matrix of distinct, spherical, gas-filled polymer cells. When a heavyweight punch lands, these cellular solids undergo three distinct phases of deformation. The first is linear elasticity. This chart maps the stress-strain relationship for cellular foams. In this initial linear slope, cell walls bend slightly, but do not collapse. As force exceeds the yield point, the curve flattens into a long horizontal plateau. In the second phase, the intense pressure causes the rigid cell walls throughout the polymer matrix to physically buckle and cave in on themselves. As the gas-filled cells flatten out, they press tightly against their neighboring cells, rapidly increasing the internal contact area within the foam. This widespread cellular deformation takes the highly concentrated instantaneous pressure wave of the punch and spreads it across a vastly larger surface area. The time it takes for millions of microscopic walls to buckle sequentially creates a physical delay, keeping the peak load away from the fist. The plateau phase elongates delta t, which reduces the peak reciprocal force that eventually reaches the metacarpals. During that single millisecond of contact, the collapsing polymer matrix actively converts the strike's kinetic energy into strain energy. This process is governed by a mechanical property known as hysteresis. Instead of storing that strain energy like a coiled metal spring, the extreme friction between the buckling cell walls dissipates the energy as heat. Engineers quantify this energy loss using the coefficient of restitution, measuring the ratio of final velocity to initial velocity after a collision. High-density boxing foam is strictly tuned to have a low coefficient of restitution. If the foam were highly elastic, it would snap back instantly, acting as a secondary hard impact against the boxer's own knuckles. Optimal energy attenuation dictates that the kinetic energy must be lost to thermal and structural dissipation, permanently removing it from the mechanical system. This chart tracks the final phase of foam deformation, densification. The stress curve spikes upward at the plateau's end. This steep vertical asymptote marks the densification threshold, where the cellular structure bottoms out and solid walls crush together. Once the material becomes incompressible, the foam ceases to absorb energy. Any remaining kinetic force is transferred directly to the bone. To prevent the foam from reaching densification too early in the collision, the internal microscopic mechanics require macroscopic external constraints. The tightly wrapped outer leather skin acts as a rigid tensile cage, bound by heavy nylon internal stitching, establishing a firm boundary condition around the polyurethane blocks. Under the tremendous torque of a 1600 Joule impact, the foam naturally attempts to expand outward. The rigid cage prevents this lateral expansion, forcing the polymer cells to compress in a straight line. The microcellular buckling protects the human hand because the macroscopic leather structure forces all compression precisely along the z-axis of impact. Zooming back out to the macroscopic level, the punch finally unfreezes, making contact and sending a mechanical shockwave through the engineered materials. Early boxers relied on vintage gloves stuffed with horsehair, a biological fiber mixture with limited energy attenuation compared to modern synthetic multi-layer matrices. Under repeated 1600 Joule loads, those loose animal fibers shifted, degraded, and reached complete densification early in a collision. Modern high-density polyurethane laminates maintain specific stiffness tolerances and cyclic durability, surviving thousands of extreme mechanical loads without failing. The physical evolution of peak striking force in the sport was strictly bottlenecked by the progression of chemical engineering. Athletes could only generate as much power as their equipment could safely dissipate. Optimizing the human body to deliver a maximum destructive impulse generates physical forces that are actively lethal to the attacker's own anatomy. The precise microscopic tuning of polyurethane cellular structures is the definitive variable preventing immediate, career-ending metacarpal fractures upon impact. A modern heavyweight punch is a symbiotic triumph of extreme human biomechanics and industrial polymer chemistry. To continue investigating the precise science behind the world's most extreme physical phenomena, be sure to subscribe to the channel.